Next talk, we have Ola Dahl, who is principal engineer at the CTO office of Enea Corporation.
Exactly.
And the talk, this is quite interesting given what we have listened before. So now we're going back to from something that's completely specialized, how we can go one step back and have it a little bit more programmable. And this has to do with a special function in multicores, which is networking. So,
thank you. Can you hear me? Yep. So this talk is about portable, accelerated networking in multicore systems, and I will approach that topic by giving you a report and a somewhat technical overview of a project where this is treated. And the project is called OpenDataPlane, abbreviated ODP, and it's an open source project driven by Linaro, which is an organization which I will describe in the presentation. First, background of Enea and the background of myself. You see we are both old. Enea was born in 1968. OSE, the sort of well-known product from Enea, the OSE operating system, was born in 1985. Now, today, Enea has a mix of software offerings in Linux and OSE, you can say, and in middleware. We also have services business, and we are distributed in Sweden and in other countries. My own background is that I joined Enea in 2013. Before that, I was in Linköping University, and before that, I was in Ericsson in Lund. And then long before that, I was in Lund University. The background for this ODP and this portable accelerated networking is the acceleration. It comes from this ever-increasing amount of data. And this picture is from Cisco Visual Networking Index. And if you follow that hyperlink, you can see that mobile data traffic in 2013 increased by approximately 80%. You can also hear, as I did from a presentation which I visited some weeks ago from Cisco, where I talked about video, which of course is the driving force. And they reported that on a peak night, the internet traffic in US, 55% of the internet traffic was Netflix. So we are really, people really like to watch TV also in the future. So that is a driving force. So logical reasoning is that the data amount increases, the speed increases, the requirements on differentiating the data when it comes into your networking box to differentiate the packets into different classes for different quality of service is also increasing. So all this data flow coming in puts demands on the hardware, so the hardware needs to change to keep up with this speed increase, and you have to invent new types of accelerators for different things in packet processing. And often when hardware changes, software needs to change. And here, of course, we have to scope the word software, so we don't talk about all software. So specifically, we talk about networking software, and we talk about the data plane, sort of the data shuffling of the networking software. So what if this networking data plane software was portable and not only making it portable in the sense that you do all functionality in software and not utilize the hardware? So what if it was portable and it utilized the underlying hardware as it changed over time? So that, of course, is a dream scenario. And if we continue to dream, if it was also open source, and if there was an organization which was not controlled by a single company that could create such an initiative, then everything would be fine. So that is exactly the ambition of this ODP project. So you could say that that is a high ambition, and you can evaluate, we have to evaluate, of course, as this goes on, how big a success it will really be. But it is existing, it's there, it has a web where you can go and look. It's driven by the Linaro networking group, and Linaro is like Linux on ARM. It started with Linux on ARM. It has grown to contain a lot of open source projects, and Linaro is divided into groups, and one of the groups is called the networking group. And this group is driving this alternative, this initiative. And it is open source. It's open source as in BSD open source. It's not GPL open source. So the idea is to have it open source, and also if people want to use it and make closed implementations proprietary, it's up to them. It's mainly software, if you use Linux, which is perhaps the main use case for this software, it will focus on software in user space. So idea is to do this processing in user space, to have a really fast access to the hardware, so we are not sort of doing inside Linux kernel work. So the idea is to sort of specify this API by making a de facto standard, which is a reference implementation which you can run on any Linux computer. And then vendors, companies that create hardware for this networking, they can choose if they want to make implementations that comply with this API. So the idea then is that if you write an application that uses this API, then that application will be portable between different system-on-chip solutions. Some words about Linaro before we move on. Linaro is a legal entity, however, non-profit kind of legal entity. It started in 2010 with ARM, IBM, Freescale, Samsung, ST Ericsson, and TI. One driving force for Linaro to start was that the Linux kernel code for ARM in this time frame was really not so well organized. It was divided into different groups corresponding to different boards, and there was a time where Linus Torvalds was also quite angry with this lack of structure of the ARM code, so he more or less threatened to throw it all out. And that is actually a concrete reason why this Linaro was founded, because now we have to clean up the Linux ARM code. So that has definitely happened, and if you look at the contributors to Linux kernel now, you will find Linaro quite high in the statistics of contributors to the Linux kernel. So Linux kernel is one big track in Linaro. There are other tracks. A word that you could look at is this Lava Lab, it says there. Lava, it's a validation framework that is Linaro guys are creating, that you can run and automatically test different kernels and different softwares and take measurements and such things. Member services is a box. You can become a member of Linaro. That means you have to pay some fee, and then you can, as a company, become a member. And there are different kinds of members. And for Enea, which I represent, we are a member of a group. So we are a member of the networking group. And member companies can also assign engineers from their companies to work in Linaro. And from Enea's side, we have 2 engineers working inside Linaro in the networking group. And we have 1 committee member, which is myself since some months back. So we are sort of 2 plus persons working with Linaro. So if we look into the box, which is the Linaro networking group, you see the member companies in that box. You also see that this group works with this ODP, but it works not only with ODP, it also works with the Linux kernel, and it works with the real-time support, which essentially means the preempt RT patch set. It also works with a feature that here is called core isolation, and that is the feature of dividing Linux so that certain processes run on specific cores, and in addition to that, to switch off the operating system tick, and it's called no hertz or no hertz full in some cases. So those are areas also where the Linaro networking group is working. You can say that for the moment, a significant amount of the work in this group is focusing on this ODP. The ODP, before we look into the details, here you can see a conceptual model of this ODP. This is a model that tries to explain the overall principle of this data plane processing. So packet comes into a system. There is a function called classifier which does a first sorting of the packets and puts the packets into different queues. Then there is the sort of the guy in the middle called scheduler, which takes packets from the queues and distributes them to the different cores. And the task of this scheduler is then to achieve load balancing for these different cores, and to pick and choose among these queues in an intelligent way. And the cores can be general purpose cores, general purpose CPUs, and they can also be accelerators like crypto, for example. And this whole processing view is sort of the base for the thinking about this software. So when you see code now and APIs, which I will show you soon, you can think of that this is the underlying processing model that implementations of this API needs to achieve. So if we look at the code, we can go and take it from the internet. Here I have built the reference implementation of ODP as it is today. The reference implementation, it's called Linux generic, meaning that this is a piece of code that can run on any Linux computer. It does not utilize, it does not assume any hardware acceleration, it just uses the standard Linux stuff. So when it does crypto, for example, it uses functions from OpenSSL library or whatever is available. So it's nothing strange. It's using auto tools, so you have to type the traditional configure and make commands, and then you can go and run different examples in the example catalog. So if we look at how typical code looks like to get you a feeling for how such ODP programs will look like if people start to develop them. You see that there is the BSD licensing clause. There is an include of the main header file. There are some defines, and you see the concept of pool. The pool is sort of a place of memory where things can be allocated from. And you can have buffer pools, and here you have something called a message pool. So you create a pool, and from that pool you allocate memory as you run your program. The barriers were mentioned several times in the previous talk. There are constructions for barriers in this ODP API, so they assume that applications perhaps want to use barriers. And you see that these data types are prefixed with ODP, so they then belong to this API. And the concept of scheduling is seen in the ODP schedule call on the last line. You call the function ODP schedule, the scheduler decides from which queue to take a thing, you get the thing to yourself, in this case it's a buffer, and you also get in the output parameter queue the actual queue from where the scheduler took the buffer. In the line before, you point out yourself, I want to take it from a certain queue. So you can then decide, I want to bypass the scheduler, I want to take it from a certain queue. This code does not run because I just took some lines. You can go to the Git repo and look at it if you follow that link. Other things that you will see in such code is that there are threads. The threads are, when you run on Linux, of course, pthreads, but there is an API on top of these pthreads so that you could run an ODP implementation also on other types of systems. One popular use case which is actually tested is that to run it what I call as bare metal, meaning that I set aside cores in a multi-core system that don't run Linux at all. They only run this networking application. And then I have some cores that I say are control plane cores that run Linux. So therefore, we don't call pthread create, we call ODPH Linux pthread create, which in this case, of course, just maps to pthread create, but in another system could map to something else. Key concepts in ODP, packets, so you can think of them as Ethernet frames coming to you from the outside world. The concept of buffer, meaning sort of an abstract representation of something that could be a packet, but that could also be something else like a timer event. For example, if you want to wait for a timeout, You say, I want to wake up after a certain time. The way that the system will wake you up is to put a timer event into a queue, and then the scheduler will take that timer event out of the queue and send it to you. So in these queues, there can live other things than packets. And for practical reasons, the packets don't, of course, live in the queues. Instead, the queues contains references to the packets, so we don't have to copy the data all over the place. So these are typically called descriptors, the things that live in the queues, and they reference to the actual data that are stored somewhere else. Just to see some more code before we continue, you can see that there is a on the third line, SHM packet pool. So here, this programmer wanted to have a pool where the packets can be taken from when they want memory. The scheduler function is called. Out of the scheduling function comes a buffer. The next function call converts the buffer to a packet. Sort of now, from this abstract buffer, give me a reference to the actual packet data that lives inside. So what this is essentially, all these queues and scheduling and taking up stuff, you can think of it as a message passing paradigm. You are passing around messages, and the scheduler takes the messages from the queues and pass them along to the different cores. So it's a message passing paradigm targeting the networking application space, you can say. And then there is the concept of packet I/O, as they call it. It's sort of representing interfaces to the outside world. So key concepts, packet I/O we have mentioned, the outside world, timers we have mentioned, the scheduler, which sort of the intelligence in the middle, classification, sorting and filtering packets, and when we talk about Linux, we also have the paradigm that these data plane threads are typically run to completion threads. So you take a data and then you run until you're finished and you give away the data again. So the goal is that on these cores that do data plane processing, we should not have any context switches in the Linux sense, and we should not interfere with the Linux kernel at all. We should only do user space processing. This is the picture again, a little bit more detailed, the overall flow with the scheduler in the middle. You can see on the right-hand side examples of functions that can be implemented in such data plane threads, like IP forwarding and NAT, and different protocols or the packet inspection or what have you. So the challenge, of course, provided that this API is good enough to use, is to then to design an application by putting such functionality into threads, which can work then in this system with the scheduler and the queues. So we don't know how good this will be. We know that it is a work in progress. We know that there have been demonstrations that we will see very soon in some pictures. So of course, is it a sort of academic goal that will never be achieved, this portable API? Can it be portable and efficient? That, of course, time will tell if it will be good enough. But the idea is to envision what we call ODP implementations, and they can then come from different vendors. They can be open source or they can be closed source. So is this just fantasy or does it work? This is a picture from a Linaro conference that was held some weeks ago. They hold these conferences in Linaro twice a year, and this was the one held recently. It's called Linaro Connect conference, and here is Cisco that are demonstrating that they run on ODP on a piece of hardware, and then they have taken the reference implementation for ODP and then have linked it to their data plane code, as they say. And they have also taken the ODP implementation for TI Keystone 2 hardware and linked it to their data plane code and run it. And they ran it as a demo on this conference. And they demonstrated, some demonstrators demonstrated packet forwarding, just packet in and out. Cisco demonstrated an IPsec example. So these are pictures where Cavium did a demonstration, and Cavium are particularly interested in this bare metal concept. So they actually compared running the bare metal scenario where Linux is not used at all on the data plane cores with using the Linux with no hertz and core isolation on the data plane course. And they said, just by a first impression, that the overhead of having Linux was like less than 10% or something like that. So they did not rule out running Linux, but I wanted to try this bare metal initiative also. The development of this is now going on in the open, so you can really follow the development, and you can participate in the development, and you can go to meetings, phone conferences that you can speak and you can influence, and you don't have to be a member of the Linaro to do that. So that has pros and cons, of course. This is a democratic development. Here you see some quotes from the mailing list. I can say that there is no Linus Torvalds-like person. So you see, people are quite polite. There are not so many flame wars, but it's also democratic in the sense that you don't know how fast it will move forward. So it's like design by committee could sort of be the bad aspect of this. So we have to see where this goes. But currently it's a work in progress. They did some statistics for the previous Linaro conference, and it's like 25-ish contributors, 50,000 lines of code, like 300-400 commits in the Git repo. So it's growing, and people are adding stuff all the time. So it's a multicore aspect, and the evangelists of this approach claim that this scheduling idea, of course, takes away most of the multicore problems with locks and things like that. And you can really say that this is the message passing advantage, that you pass around messages and you don't have to use a lot of locks. Still, there are locks that you can use in the ODP API, like spin locks and barriers and such things. And then there is the Linux functionality that you utilize to get a good isolated performance of the data plane processing. This is a picture that I took from Cisco's presentation. You can look at Cisco's presentation here. And by the way, you can look at the whole conference, Linaro Connect. It's very open. All the presentations you can look at the videos. And if you want to follow the next Linaro Connect, you can also do it remotely, live. There is typically live video from all the sessions. So it's really an open happening, this Linaro Connect. So this is the Cisco presentation where they did IPsec, and they said that, okay, we have linked in this ODP library, we utilize the hardware. If we compare utilizing hardware with not, we have like a 22 times speed up, etc., etc. So they make demos. They do some not only just packet in and out, they do some processing with crypto. Other vendors do similar things, Cavium, Freescale, and Avago. So you can say, if you want to judge the popularity of this project, that vendors are, at least they are creating demos, they are showing up at such conferences, they are showing us their demos. So as time goes on, this ODP project, which is now being developed in the open, as I said, the next milestone is to have something called 1.0 end of this year. And the mantra for that release is good enough for evaluation. So if you are a vendor, or if you're interested in doing networking systems, it should be good enough for you to judge if this is interesting or not. And you could try out to make implementations. Then they have higher ambitions for the end of next year. I say, if you want to make a product end of 2015, this ODP concept should be good enough so that you can do that. Final word, on the FAQ, if you want to create such a thing, the first question is perhaps why this and not DPDK, and that it could be a long discussion, but here is a slide that just tries to illustrate the ODP standpoint on that question. The ODP standpoint is that ODP is an API which in some sense is generic and perhaps not tailored to specific network interface cards. So they have actually created, there is a reference implementation of ODP that uses DPDK inside. It's called ODP DPDK on this Git repo. So the mindset that ODP wants to convey is that the DPDK is one implementation, so ODP API sort of hides the DPDK API. And that is then to be considered as one of the different kinds of implementations that can exist. So here are some links if you want to pursue further. The ODP stuff is very open. Linaro Connect I can recommend. There is a lot of interesting things there. And if you want to look at or join the mailing list, you can just follow that link. So thank you for your attention.
Thank you. Any questions?
Thank you for your talk. One question about the implementation of the Cisco. I know maybe they didn't talk about it, but it's funny that they put in, they showed the hardware implementation. You said it was 22 times faster.
Yes.
If you use the hardware
If you use the
acceleration.
Exactly.
But do they compare that with their own reference implementation using their complete stack compared to the ODP stack using hardware?
I think they compare because there are two ODP reference implementations, so to speak. One is the Linux generic, which is software only. The other ODP implementation is done by a guy from TI, utilizing the TI hardware. So they put those two ODP implementations.
Okay. So there's no third, which is their exact implementation?
And then to those, they linked their own stuff.
Right.
To the respectively.
So I guess my question is then, do you see ODP performing better or performing very similarly compared to their own stack? Do they see it performing similarly to their own stack?
They did not say anything about that.
Okay.
But
Okay,
they said that they welcomed such an initiative because they talked about the cost of moving between different generations of ASICs. So they really appreciate if there would be an API.
Okay, thank you.
Anyone else? I cannot see any. So we're good for coffee. Let's go.
Thank you.
Thank you.